Hello, everybody, and welcome to this short talk on the geology of La Gomera, one of the Canarian islands. It's a talk about the geology from the perspective of a tourist, but it's a tourist with a view to the landscape, because in the landscape, the whole clues to the geology are contained. So the tourist would look at the landscape and begin to pick up an understanding about the broad principles of the geology of this island. But let's just remind ourselves, first of all, where the Canaries are. They are off the west coast of Africa. And this is Morocco. There's the Straits of Gibraltar up there at around latitude 28 degrees north. So these are the islands here. And what about La Gomera itself? Well, it's one of the smaller of the Canarian islands. It's sitting just there in the archipelago. It's the second smallest, only El Hierro is the more smaller of the islands. The overall geological controls on the whole of the Canaries is a series of within plate magmatic events. It's what we call hotspot magmatism, like Hawaii and like Madeira. And this is magmatism that takes place within plates rather than, as it says down there, at plate boundaries, for example, mid-ocean ridges where we generate new oceanic crust, or at subduction areas where we are consuming plates, tectonic plates. These are being recycled, and there is magmatic activity associated with that recycling of the tectonic plates. Good example is North Island, New Zealand. Now, these Canarian islands like Hawaii, Madeira, the Azores, for example, are all classed as volcanic oceanic islands. And they all follow a very similar history broadly. They start off with a submarine stage as the volcano erupts on the seabed. More and more lavas build up, and eventually the edifice builds up to sea level. Once we get to the sea level stage, we move into what's called the shield building stage, and this is where the magmatic activity really takes hold. The activity is subaerial, and we build vast amounts of lavas to build the shield of the volcano. We then pass into a phase of volcanic quiescence. During that phase of quiescence, erosion takes place. Dependent on the amount of time, determines the amount of erosion that has taken place. Then these islands go into a phase of resumed volcanic activity. Now, sometimes it can just be a continuation of the shield building events, or it can actually be what's called a rejuvenation stage. And when we go into the rejuvenation stage, there is a change in the thermal dynamics of the magmatism. And this results in a different composition of the magmas that are being erupted. So we can identify rejuvenation stages and separate them from shield building stages. So what about Canarian magmatism? Well, it's ongoing. We have events such as the Lanzarote 1739 eruptive phase, quite a large eruptive phase where a lot of the island was built. There's also, I believe, an episode in somewhere around 1840, but it was somewhat more minor. Tenerife, the last activity was in 1976. El Hierro, with just offshore magmatism, 2011 was the last time that erupted. And for La Palma is currently active from the Cumbre Vieja vent. So that's ongoing. But on La Gomera, the activity ceased at about 4 MA ago. So 4 million years, we've had 4 million years of volcanic quiescence. And all the Canarian islands are characterized by numerous volcanic edifices. Lanzarote is a perfect example where, well, the whole island is full of volcanic cones and craters. Teide on Tenerife, for example, is another good example of the edifices that we can find. La Palma as well. Now, what about La Gomera? Well, this is La Gomera from the sea. One of the air corridors into Tenerife passes south between La Gomera and Tenerife, so it gives you a good opportunity, if the weather's fine, to look at the island. That's La Gomera. And from the sea, the shape of the island actually gives away a bit of the geology, because this is like an inverted pudding basin type of picture. And this is characteristic of a volcanic shield. So just by looking at the island, you can get some idea about the geology. There's a Google Earth map, a picture of La Gomera. It's not a big island, as I've mentioned. And if we compare it with the island of Arran, for example, we've got a similar size. Right, let's look at what the island looks like itself, the physiography of the island. This is its neighbor, that's Tenerife. This is the sound that one would cross on the ferry to arrive into the port of San Sebastián de la Gomera, and then one would take a vehicle from there. We'll go on a little drive in a moment, but let's look more at the shape and the characteristics of the island. It's got quite significant sea cliffs. The whole island is surrounded by quite massive sea cliffs. There are some very good examples of the sea cliffs. Very precipitous in most places. The whole island, this whole pudding basin, the whole shield, volcanic shield, has been eroded significantly by a number of deep ravines and drainage systems. These are called barrancos. And as we go up higher onto the top part of the island, the maximum elevation is somewhere around 1490 meters above sea level. As we go up onto the higher parts, we begin to find these upstanding units in the landscape. This is one of these steep ravines, these barrancos. There's more we'll see in a moment. So the tourist would arrive at the port of La Gomera, San Sebastián de la Gomera, and then drive up on one of the two roads from the port. And here's one of the roads coming up onto the central plateau. It becomes much more rocky higher up. This is what it looks like as we're climbing up the road. And near the highest points, we've got quite rugged topography, but there's also quite a lot of indication of geology there. This is columnar jointing. We'll be talking about that in a moment. And right up on the highest parts, we've got these upstanding masses in the landscape, quite prominent across the central plateau. So the central plateau, that's the central plateau up there. And these are these deep erosional barrancos. There's one down there, and there's another one down there. There's a significant one coming all the way down there. There's another one coming down there. And this is the classic view of the erosional features of the island, these very, very steep-sided barrancos. The other thing that a tourist would notice as they wandered around the landscape would be these steps in the landscape, very, very characteristic, very, very noticeable. Right across the whole of the island, these steps in the landscape. And of course, this is the giveaway for the geology of the island. There's more steps in the landscape here. Numerous features across the whole of the island. So what about the broad geological features of the island? Well, as I've said, is built predominantly of a series of lavas, and these are both of Miocene age and of Pliocene age. We've also got intrusive domes and plugs and bosses exposed at higher elevation, as we've just seen. There's a whole series of minor intrusive dikes, both of Miocene and of Pliocene age. And the interesting thing about La Gomera is that it's had the longest period of volcanic quiescence of the whole of the Canarian islands. And so it's got the highest level of erosion, which means that erosion has cut down through early geological features and allows us to look at these features in a little bit more detail than we can do, for example, on Lanzarote and Tenerife. So let's look at the geology. But before I talk about the rocks, there's something quite significant about the vegetation. So I want to take a couple of minutes just to look at the vegetation of the island, and you'll see why it's significant in a moment. If we're down from sea level to about 500 meters elevation, we're into a semi-desert type of vegetation. We've got prickly pears there, agaves and palms. There's the prickly pears, there's some broom there, there's euphorbias, there's the agaves there. There isn't a continuous cover of vegetation, so it's classed as semi-desert. But as we rise up to around 800 meters in elevation, we begin to see a greening of the landscape. We begin to see a whole change to the perspective. It's becoming green. At around 1,000 meters, we're getting grasses in the landscape. We're getting heathers as well. Some of these are small heathers. You've still got the agaves and things of the semi-desert vegetation, but it is becoming much more lush. And that lushness continues by about 1,100 meters, where we've got pines, pines growing here. We've still got the smaller vegetation, the palms, for example, down there. By the time we get up to 1,200, well, full grass cover, and these are broadleaves. This is Castaña hispanica, the Spanish chestnut. There's also beeches in here as well. We've still got the palms, but it's becoming much more lush. By the time we get up onto the very top, we have this. This is the reason I'm taking you up here, because this is a UNESCO World Heritage Site. This is a laurisilva forest. It is a forest composed of primarily laurel type plants. And it is a very humid, a very damp environment up here. And all the plants are designed to be able to cope with quite a high level of rainfall, leaves that shed water. And there's an understory, as you can see here, of ferns and mosses and a whole range. So this is a very, very special ecosystem. And the laurisilva forest of La Gomera is the best. The next best, you'd need to go to Madeira to find another good example. But across the whole of the Macronesian islands, laurisilva forests predominate as long as we've got reasonable altitude, because the reason that we've got those forests here are, well, it's a cloud horizon. And if we've got a significant altitude, the trade winds are intercepted by the altitude and they will drop their moisture. So it's a cloud forest, basically. And places like Hawaii have got the same sort of features as well. So higher up, higher elevation, we have these very lush forests. So that's just a little aside while we're being a tourist on La Gomera. Let's now look at the geology and look at its volcanic history. Well, as it says there, we don't have any reliable evidence of the pre-shield, the submarine stage. But the main geology that we do see is the Myocene Shield stage. And the Myocene Shield stage was formed somewhere around 12 million years ago in the late Miocene. And it's a series of, as it says, seaward dipping, shield building, basaltic lavas and pyroclastics. Then we have a post-shield erosional stage. So we've lost the volcanic activity in Miocene. We've gone into an erosional stage, and that erosional stage lasted for about 4 million years. No volcanic activity during this period. And at that time, there was quite significant canyon erosion of the shield. And that's important, as we'll see in a moment. And then in the Pliocene, probably somewhere around 5 million years ago, there was another short phase of Pliocene activity, but that activity ceased about 4 million years ago. And during that Pliocene eruptive phase, we had a series of basaltic lavas formed. Also, there was opportunity for the magmas to differentiate somewhat into slightly more felsic material and generate these felsic or more felsic plugs, bosses, and domes as minor intrusives. And also, we have a whole series of minor intrusive dikes, both of Miocene age and of Pliocene age as well. So that's a broad picture of the geology. So let's now look in a little bit more detail about these at these various events. So let's start off with the Myocene Shield volcanics. This is a series of shield volcanics. These are pyroclastics. This is predominantly a series of lapilli, and the eruptions from both the Miocene and the Pliocene phases were strombolian. So that means there was not significant explosive power in the eruptions. There was reasonable amount of power, as we'll see in a moment, but the whole volcanic phase, both Miocene and Pliocene, characterized by strombolian activity. And this is a series of strombolian pyroclastics, lapilli, as it says, and these are part of the shield building stage. And you'll notice that they are dipping, and they dip seawards, and the sea is to the left of this picture. So the shield building lavas dip seawards. There's a series of shield building lavas there. So these are the Miocene lavas. The sea is to the left of this picture. Series of dipping Miocene lavas there of the shield. There's another series here. There's the dipping shield volcanics there. These ones up here are the Pliocene, and we'll talk about those subsequently. If you're a tourist with an eye to the geology, do make sure you get yourself a balcony that overlooks a view such as this. This is from my own balcony, so I could sit out and look at the amazing geology. Here's another series of these seaward dipping shield building lavas. And another series here. This is mentioned the deep erosion caused by this volcanic quiescence, and the opportunity to delve deep into the geology. Well, this is a perfect example here where we've got the Myocene shield lavas nicely exposed for study. There's another series up here. See these seaward dipping lavas, and here the seaward dipping series of lavas coming up here, and they are in contact with the horizontal Pliocene lavas at about that level there, somewhere along there. We'll examine those contacts in a moment. Another series of seaward dipping lavas there. Series here. We're looking sort of obliquely along the strike of these lavas. So they're dipping down to the right of the picture. We're looking along the strike of these Myocene shield building lavas. So here we've got shield building lavas dipping. See is on the left-hand side here. And you might be beginning to be wondering what these horizontal Pliocene lavas are doing surrounding this lump of the Myocene shield. Well, I'll explain. This was originally a continuous cover across the whole island, as I've mentioned. But then during the volcanic quiescence after this Miocene phase of eruptive activity, the whole area was then subject to erosion, and deep canyons developed, cutting into the shield. So here's the shield here. And what happened was that when the Pliocene magmatism restarted, these canyons were filled initially by the Pliocene lavas. And so here and here, these were originally canyons cut into the Myocene Shield. They then became filled subsequently with the Pliocene lavas. And I can explain that in this little diagram here. We're looking at the same picture. So these are the Myocene Shield lavas. And these were canyons carved post-Miocene, carved into the shield. And then during the Pliocene resumption of magmatic activity, they became filled, canyon filled with the Pliocene lavas. So that, I hope, will explain what this chunk of the Myocene Shield is doing sitting there. And I want to take you up to here, this point up here, and we'll then look across down in that direction. Now here we are, we're now standing on Myocene Shield lavas. They are striking in this direction. We're looking obliquely along the strike of that little unit there. The strike is along here, and these are dipping that way to the left of our picture. So the whole area at one time would have been covered like this, covered with this Myocene Shield. But then during the volcanic quiescence, big canyons were carved out. And then subsequently, these canyons were filled, these barrancos were filled with the Pliocene lavas, and there are the Pliocene lavas. This white line along here, this was originally an erosive contact between the Myocene Shield and the canyon, the barranco, as it was pre-Pliocene. But then during the Pliocene, it became filled with the Pliocene lavas. So hopefully that will explain the relationship between the Myocene Shield and the Pliocene lavas. So let's carry on with the looking at the Myocene Shield. Let's look at a little bit more detail at the eruptive stage. The lavas were, I say, basaltic. They're not exactly basalts. Can't really classify them, strictly speaking, as basalts. They're called ankaramites, which really means they're sort of basalts, but they've got a lot of pyroxene in them. And these, there were numerous of these shield building flows, and also horizons of tephra, which were composed of ash, cinders, lapilli, and also a series of volcanic bombs and blocks, which we'll look at in a moment. So in a bit more detail, this is a succession of, as your meter scale up there, a succession of tephra. These are lapilli, 5 to 10 centimeter chunks of lapilli. There's another section of lapilli there, it's about 1 meter in height up here. And here we've got some strombolian airfall, pyroclastics. These are ashes and fine lapilli. For scale, the tripod is 40 centimeters in length. There's a tripod there, 40 centimeters. Now this synclinal appearance is really just topography fill. So these ashes are filling in topography. They're banking up against slightly higher areas within the topography. And then on top of these series of pyroclastics, ashes and lapilli, we've got basaltic lava flows. So there's a basalt lava flow there overlying this series of tephra deposits, pyroclastic tephra. There's another series here. We've got some tephra horizons down there. Then a rubbly base to a more coherent lava flow, rubbly top, and then another flow, and this continues up this little area we're looking at. So numerous flows of these basaltic composition shield building lavas. Now these areas here, these chunks, these are volcanic bombs. This is a horizon of tephra, but these are volcanic bombs within the tephra. So these have been hurled out explosively from our volcanic vent, strombolian activity. There's some more volcanic bombs here. These are 40 to 50 centimeter chunks here, so quite significant pieces. There's more of it there in these tephra horizons. There's more there. Again, we've got the tripod 40 centimeter scale, so quite large chunks blasted out from the volcano. And another series of this picture here. So these are all components of the shield building stage. Now, interestingly here, we've got, in this area, we've got those steeply dipping series of lapilli. These are dipping to the left of the picture because the sea is on the left-hand side. And these horizons come up to this level along here. Go into there in a bit more detail now. So these horizons here are contiguous with those 20 to 30 degree dipping units. But here, this horizon here and the ones above are all shallow, almost horizontally dipping units. And this line along here, this white horizon, this line is the unconformity between the Myocene shield building lavas and the subsequent Pliocene lavas. And the white line is actually in this area here is a series of zeolites. It's a zeolite horizon. So this is the unconformity between the Myocene shield down there and the Pliocene eruptive phase here. Right, so that was the Myocene shield volcanics. Let's now look at the post-Myocene, the Pliocene eruptives, which were, remember, post-shield. And as part of the inventory of volcanic activity, we don't just have the eruptives, we've got the intrusives as well. So first of all, we'll look at the Pliocene eruptive stage. I've seen this slide before. These are the Myocene, and this horizon here is the junction, the unconformity between the Myocene lavas and the Pliocene post-shield lavas up there. And this picture here is a series of these Pliocene post-shield lavas with very pronounced columnar jointing developed at numerous horizons, as you can see there in this landscape view. The thickness of these horizons here is probably about 10 meters here. So these quite thick lava flows. There's another series of nicely columnar jointed lava flows there. There's some trees and things in the background and a telephone mast up there for scale. And there's a trail along there for scale. So these are the Pliocene horizontal eruptives. Nicely columnar jointed. This is quite a large flow, thick flow. It's about 8 meters, 5 to 8 meters thickness there of these basaltic lavas. Again, these are ankaramitic basalts. Here's a nice example of a lava flow. I can find my pointer. A lava flow here, which is being fed by a dike, and the dike is cutting through earlier Pliocene lavas and is feeding this more coherent, more massive lava flow here. We'll go into that a little bit more detail. So there is the feeder. So at this point, it's a feeder dike cutting through earlier Pliocene lavas to feed this lava horizon along here. So that's a nice example of a feeder for these eruptive horizons. Again, in the landscape, looking at more of these steps in the landscape. In a little bit more detail, we do have horizons of ashes and tephra, as this slide here shows, passing up into a rubbly base and more coherent of the Pliocene lavas. And we have pahoehoe developed as well in places in the Pliocene eruptives. This is a picture of these ankaramitic basalts, and you've got your 1 centimeter scale up there. This is a pyroxene. These are all pyroxene crystals in a basaltic ground mass. So that's just a view of the type of rock that we're looking at. So these are the eruptives. These are the volcanic units. The other significant feature that we find throughout the volcanics are these massive collapse structures. The lava pile with all these pyroclastics and the rubbly bases, rubbly tops, they're not very strong, they're not very structurally stable, and at times they collapse. And this is a massive collapse on the western coast of the island, and we've gone down somewhere in the order from here where I'm standing down to sea level down there. This is about 1 kilometer. So 1 kilometer of material has collapsed. 1 kilometer of the volcanic pile has just collapsed and gone out into the sea. And these collapses are characteristic of all these volcanic islands. As I say, the volcanic pile is not stable. The classic example of collapse is on Big Island in Hawaii, where the debris apron out onto the continental slope covers an area, well, it extends something like 16 kilometers from the island itself. So it gives you an idea just how significant these collapses can be. And of course, when these collapses happen, they generate massive tsunamis. And we're beginning to record these across the globe as well, and relate these to various collapse events on these volcanic oceanic islands. So that's the Myocene eruptives. What about these intrusive elements that we've got? We've got an intrusive thing there. So let's look at the intrusives. As we come up onto the higher parts of the island, mentioned earlier, we're beginning to see, well, there's nicely columnar jointed, but these big areas of well, these are intrusions, basically. And as we come higher up, they are more pronounced. Columnar jointed, you can see the columnar jointing along there. Some nice columnar jointing on this one here, on this plug, this boss, and there, some nice columnar jointing all the way down there, and columnar jointing here. And these are more felsic, so the magmas have been able to differentiate somewhat and to generate slightly more felsic, more viscous phonolites and trachytes, which don't flow so well. And so when they are erupted or intruded, they tend to form plugs and bosses rather than flows. And that's what we're looking at here. So these are congealed lavas, and they've just been sort of intruded at relatively high level, relatively shallow level, but haven't flowed. And so the whole of this is the plateau at the top, the whole of this plateau is dotted with these slightly more viscous lavas that haven't flowed. Let's now draw our attention to this one here. This is La Fortaleza de Chapudi. Chapudi is the town just there up on the plateau. So we'll go and look at this one in a little bit more detail. Here we are moving slightly closer into it. You can see some nice columnar jointing developed. And if we go in even more closely, very nice columns being developed there. We've got tourists on the trail. There's a tourist there for scale. The tourist bus has just arrived, and I'm getting out of the way. I've been up here already. And closer up still, some really nice columns in this, what is a trachytic, a trachyte. So it's a slightly more evolved from basalt. It's becoming a trachyte, but viscous and is not flowing like a basaltic lava would flow. And this is looking down from the top at the columns. These are sort of vertically jointed sort of columns. So there are some quite nice columns developed in places. If we look from the other side, this is coming around the corner. That last picture, I'm getting my pointer. That last picture that was taken there. So we've come around to the side, and the interesting feature here is this. We change our view even more, and what this is coming down this canyon, this gully here. This is the feeder. This is the feeder conduit up which the trachytic magmas were passing before they intruded at a shallow depth within the overlying lavas and then congealed. So this is the feeder, and this feeder goes from here. The elevation of this La Fortaleza de Chapudi is something in the order of 1,1200 meters, maybe 1,300 meters above sea level. This feeder dike goes right the way down about 1 kilometer, and we can look down from that top part, and that's 1 kilometer, and all the way down we've got this trachytic feeder that is feeding this dome, this plug. So it's really fascinating to be able to see this, and this is the advantage that erosion has given us, being able to look at in quite depth, literally, at the various processes that have formed the island. And finally, we have this series of minor intrusive dikes. We saw earlier that little dike that was feeding a lava. So all these dikes would be feeding lava flows. These would be the feeders for the lava flows. And as I mentioned at the start, these are of both Miocene age, so these would have fed the Myocene Shield from deeper down, and also the Pliocene lavas as well. So these are we're looking down into the deeper parts of this volcanic activity and looking at the feeders. There's a nice one through there. There's another one through there, cutting through shield lavas. We've got another one here, cutting through more of the shield lavas. There's one here, again, cutting through this Myocene Shield lavas down there. And there's one up there. And there's another little dike cutting through more Pliocene lavas there. So a whole volcanic succession there from the lavas through to the feeders and the plugs of a more viscous lava magma. So in conclusion, and this photograph here really is a summary, a concluding summary of the geology of La Gomera. We're standing on Myocene Shield lavas. These are dipping to the left of the picture. Down in this barranco here, we've got seaward dipping, and the sea over there is to the right-hand side. These are seaward dipping Myocene Shield lavas, and these are capped by the Pliocene lavas along here. And into the Pliocene lavas, we have on the top parts of the island, we have these intrusive, more trachytic, phonolithic plugs, bosses, and features of the intrusive phase of Pliocene activity. And finally, the intrusive suite of dikes of both Miocene and Pliocene age. So that is effectively the geology of the island of La Gomera. And so as the sun sets on La Gomera, it's actually setting there over the island of El Hierro. I hope you've enjoyed your geological tour of the island of La Gomera, and thank you for your attention.